Temperature. Temperature is a fundamental concept in atmospheric thermodynamics. Temperature is a scalar. That is, unlike a vector, it only has a magnitude. It does not possess a direction. But temperature is also a scale. That is, it doesn't have dimensions. It's not measured in the same way like length or mass. Temperature is defined as a scale between two fixed points, typically the boiling and freezing of water. The zeroth law of thermodynamics states the following: that when each of two systems is in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. And we can measure the thermal equilibrium, or the distance from thermal equilibrium, in terms of the concept we call temperature. Consider then two bodies. The red body is hot and the blue body is cold. Note that we don't describe temperatures as hot or cold. They are high or low, large or small. Each of these two bodies under consideration has their own thermal energy, which is a measure of the distribution of velocities within the gas or the solid or whatever that these bodies consist of. As a measure of this distribution of velocities, we may ascribe a macro quantity, meaning that we don't care about the micro details. And this macro quantity we refer to as temperature. And so the hot body has a large temperature T1, which is greater than the temperature of the cold body, T2. When we bring these two bodies into thermal contact, that means that heat is able to flow between them. Now, to be particular, there is no such thing as heat as such, or heat flowing. Heat is not a substance. What it does measure is the thermal energy, in the case of heat, and the exchange of thermal energy, or the energy exchange, in the case of heat flow. And that's a measure of how the molecules interact. So in the hot body with a large temperature, there's going to be a greater velocity, or the value of the velocity distribution is larger than the cold body. So the net result will be that molecules in the hot body will exchange energy with the molecules in the cold body, such that the energy content of the hot body will go down and the energy content of the cold body will go up, and that will be measured in terms of the temperature. So expect the hot body's temperature to decrease and the cold body's temperature to increase. When we do that, what we can see is eventually the zeroth law states that we will get thermal equilibrium. That is, the two bodies that are now in thermal contact will have the same distribution of molecular energies, and we can measure that in terms of this macro quantity temperature. So T3 will be less than T1 but greater than T2. And you can see over time the heat exchange, or the energy exchange, between the hot body and the cold body decreases until it's essentially a net transfer of zero across the interface between these two bodies. As we discussed before, we measure temperature in terms of a scale. So specify two fixed points. They're temperatures which can be reproduced as specified physical conditions of certain substances. And in terms of water, for example, it's boiling and freezing. The numbers are assigned to these 2 points, and then you specify the number of divisions between the 2 points. So for example, in Celsius you have 0 is freezing, boiling is 100 degrees, and then you divide through by 100 to get 1 degree Celsius increments. So we must speak of divisions and not of units of temperature per se. So for example, 20 kilograms is twice as heavy as 10 kilograms. 20 meters is twice as long as 10 meters. But 20 degrees Celsius is not twice as hot as 10 degrees Celsius. They're just the 10th and 20th subdivisions of the Celsius scale. And as I've already stated beforehand, temperatures are not hot or cold. Temperatures are either low or high. It's objects that are hot or cold. Here we can see the temperature scales. The two most common ones used in terms of day-to-day temperature forecasts are Fahrenheit, mostly in the United States of America, and Celsius, everywhere else. And it's measured, the two fixed points are the steam point and the ice point. In terms of Celsius, there are 100 divisions between 0 and 100. In the case of Fahrenheit, there are 180 divisions of Fahrenheit between 32 degrees Fahrenheit and 212 degrees Fahrenheit. And one can convert between one and the other by the following equation shown there, that degrees Fahrenheit are equal to 1.8 times degrees Celsius plus 32 degrees. When we're looking at forecasting applications, for example using what's known as aerological diagrams, which reproduce atmospheric processes, we're going to use degrees Celsius. But when you're using looking at temperature in most equations, we're going to use degrees Kelvin, which works on an absolute scale. So take 273.15 and add it to degrees Celsius to get to degrees Kelvin. Hence absolute 0, or 0 degrees Kelvin, is minus 273.15 degrees Celsius.